So I've drawn a big nasty molecule underneath my previous azo dye. So organometallic dyes, these organic compounds with metals in them, are still going to obey this molecular orbital theory approach to looking at where the energy comes from. Now, the big difference between this organometallic complex and something like an azo dye is, with an azo dye, typically that HOMO-LUMO gap are both bonding and antibonding. Now, there are exceptions to what I've just said, so I'm going to qualify that here and now. But generally speaking, when we have something like an azo dye, we've got this symmetry between the HOMO and the LUMO. And it's centered around the atomic orbital energies. So as we decrease the HOMO, we're typically increasing the LUMO at the same rate. So as we drop the HOMO, we're going to get the LUMO increasing just as much, and this kind of creates a problem because we're not moving one independent of the other. They're having to move together. Now, organometallic complexes are very different because, generally speaking, and yes, there are exceptions to this, we don't see a HOMO-LUMO gap due to a bonding and antibonding orbital. What we actually see with the metal is that our HOMO are actually non-bonding orbitals. So because of the symmetry of most of these transition metal complexes, the electrons that are in the highest occupied molecular orbitals are just basically the energy of the metal itself. And that's not going to shift regardless of what we do to the molecule because these are non-bonding. They don't have the symmetry to participate in the reaction. The LUMO itself are the antibonding orbitals, and they are the antibonding orbitals between the metal and the rest of the complex. So here, where our HOMO and LUMO were centered across the whole molecule, the HOMO and LUMO for organometallic dyes is centered around the metal itself. So that's the big difference. Color chemistry occurs across the whole molecule here. Here it's specialized just to the particular organometallic, just to the metal itself. Now, the HOMO, because it's not bonding, is not going to move, but we can definitely shift the LUMO. We can shift it by changing the substituents on the ring. So with organometallic dyes, typically we change the color just by changing the gap between the LUMO, and this gives us a lot more control. We're not bound by this kind of like symmetric move of the HOMO and the LUMO. The reference to the metal isn't going to change. That LUMO is going to go up and down, and this kind of gives us a lot of power because we can change the metal. Now, there are limitations to what metals you can incorporate into the molecules. Yeah, go take inorganic chemistry. But generally speaking, we can dial in what that baseline energy is by changing what the metal is, and we can have a lot more control because we're only changing the energy of the LUMO. Now, an additional advantage of this, which is something we really don't see as much with this, I mean it does occur with this, but not as much with this, we can attach this, if we just use single bonds, we can attach this to a surface and basically not change the color of the dye. Because unless we have a conjugated pi system connecting whatever this is to whatever we're attaching it to, this really is not going to have a major effect on the ring. Now, you can kind of sort of do this with azo dyes, but again, because you are affecting both the HOMO and LUMO, there's a lot more sensitivity to what you're doing. A shift in the LUMO is going to have a corresponding shift in the HOMO as well. So this is what's kind of cool about, to me, color chemistry. Organic chemistry will tell us how to make these compounds, but it cannot describe the color chemistry that's going on. And this is going to be a stepping off point then for a reason for needing molecular orbital theory. These types of predictions are made by molecular orbital theory. They explain what's going on with the color chemistry and how we can change the colors of these dyes. So I hope you've enjoyed these little vignettes on how color chemistry comes about. Again, I find this incredibly interesting, and I think it does a good job of showing how organic and inorganic chemistry can actually couple together and be harmonious for once in their careers. So hope you enjoyed it.